Hello everyone, welcome back for our next installment of Wait, What Do I Do? A quick tutorial. This time we're going to be covering our independent groups t-test. So this is the practice problem that we did in class. This was your practice with a partner participation. That's a lot of P's. A team of researchers is interested in the effect of expressive writing about traumatic events in one's physical health. 20 students are recruited to participate. 10 in the expressive writing condition, where the student read about their feelings, and 10 in the control group, where students wrote about neutral events. You can already see this is an independent group, right? We have two independent groups looking at two different things. 1 month later, the students rated their physical health on a scale of 0 to 10, very poor health to perfect health. Does expressive writing affect physical health? We're going to use a p-value of 0.05, so our alpha is 0.05, and we're going to do the 6 steps of hypothesis testing. Notice, as we discussed in class, that this is not a directional hypothesis. Does expressive writing affect health? It doesn't say it improves it. It doesn't say it makes it worse. It just says that it's different. And so this will be a two-tailed test. So step 1, we're going to restate the research and null hypothesis about the two populations. First, we need to know who those populations are. So students who engage in expressive writing is our first population, and our second population is students who write about a neutral topic. Our research hypothesis is students who wrote expressively will rate their health differently than those who wrote about neutral events. And we need that mathematical expression as well. So the population mean for the expressive group minus the population mean for the neutral group will not equal 0. Remember here, because we're comparing those two groups, we're comparing it against this idea of no difference. And so for our research hypothesis, we'll say that there is a difference because that's what we've written out. So it's not equal to 0. And our null hypothesis will say that there is no difference. So our null hypothesis, students who wrote expressively will rate their health the same as those who wrote about neutral events. If we subtract those two population means, we'll get 0. So again, both that mathematical expression and that written expression is going to be important. You guys did wonderful on this before, so let's just keep up the good work. Step 2. Is where we have a lot of our changes for the 6 steps of hypothesis testing, just because we're going to have to estimate that standard error. Other changes, again, from z-scores, it's going to be similar to our single sample t-test, where it's our distribution of differences between means. It, however, is t-shaped because we're doing t-tests. And which particular t-distribution it is degrees of freedom 18, right? So you have to tell us which one by telling us that degrees of freedom. Remember, that's going to be calculated from our degrees of freedom total. We have to calculate the degrees of freedom of each of them independently. So group 1 had 10 people, group 2 had 10 people. That means each of those had a degrees of freedom of 9. Independent of each other, and then we put them together after that. So that's how we got that 18. Our mean of this distribution is 0 because, again, we're comparing against this idea of no difference. So if you think, if you look back on on step 1, right, we said there's no difference between those populations in the null hypothesis and that they'll be equal to 0. That's where we got that 0, this idea that there is no difference. And again, we're going to have to estimate that standard error based on our estimated population variances that we'll do from each sample. Again, these are our skills from chapter 4 and chapter 7. So we have to first calculate the sums of squared for each of these. If this is where you're getting caught up, please just go ahead and listen to this, but also go back and review that sums of squared video that I also have posted both in eLearning and on the YouTube channel about how to use these tables to calculate a sums of square. Sums of square is going to be something we use again and again and again and again. And so we really want to make sure that you're comfortable with calculating those sums of squared. Again, there are formulas that you can use. I just think it makes a little bit more sense at this stage in our understanding of statistics to do these tables, and it helps kind of keep track of all of our numbers. So we'll take each of our groups. I've already given you the mean. So the mean of our expressive group is 79. The mean of our neutral group is 68. And we're going to subtract each of those individual scores. So somebody scored a 77 in the expressive group on their physical health. And we're going to subtract that mean of 79. And that's where we get that -2. Somebody scored a 88. And we're going to subtract that mean. And that's where we get the 9. Somebody else scored a 77. And et cetera, et cetera. So we're just going to go down and we're going to take each of those individual raw scores from that data set and subtract the mean from it. Once we've done all of that, we're going to square each of those values. So -2 squared is 4, 9 squared is 81, -2 squared is 4, 11 squared is 121, -11 squared is 121, -5 squared is 25, -17 squared is 289, 14 squared is 196, 3 squared is 9, and 0 squared is 0. And because this is sums of squares, we just add them all together. We add all those squared values together. We get 850, and that is our sums of squared for the expressive group. We're going to do the same thing for the neutral group. Our mean there is 68. Again, those X values are individual scores, and we're just going to subtract each of those individual scores. We're going to remove the mean from that, subtract the mean from that, and that's where we get these values. We'll again square each of those and add them together. That's how we get our sums of squared for our neutral group. Again, if this is where you're getting caught up, I would recommend pausing here, maybe going back and looking at that how to calculate that sums of squared video. That's both, again, on the YouTube channel and posted with our Chapter 4 content in supplements so that you can get a little bit more confident. That's going to be a little bit of a smaller data set, and so it's maybe not as many numbers to kind of get startled by. Also, please make sure to reach out if you are in one of my classes to a member of your teaching team if you're not comfortable with this material, and we can get you comfortable with this material because this will be really, really important. Once we have those sums of squared calculated, we can use those to then estimate our variance for each sample. Again, this is an independent groups t-test. So first we have to calculate each of these independently. So we calculated the sums of squared for expressive independently, and we're going to calculate the variance for expressive independently. Our degrees of freedom for expressive is 9. Our variance will then be 94.44. Again, using our sample variance formula, sums of squared divided by degrees of freedom. We had our sums of squared for the expressive group of 850 divided by our degrees of freedom expressive, which is 9. Remember, we want those to match up, right? So that's why we label these things, because we're always going to use the degrees of freedom that goes with the sums of squared that are the same name. So we get our estimated variance of the population based on the sample of 85 divided by 9, which gives us 94.44. We're going to do the exact same set of steps independently for the other group, for our neutral group. Again, we have to do each of these independently. Our degrees of freedom neutral is 9. Our variance would then be 111.33. Again, we get that by taking our sums of squared and dividing by our degrees of freedom. Our sums of squared we calculated previously was 1,002, and we're going to divide that by 9. That gives us 11.33. We're still in step 2. We're still just estimating the standard error here. Again, first we have to do each of these independently before we bring them back together for that estimated standard error. So now that we've calculated them independently, we can bring them back together. For that standard error, remember, we're going to divide it by the number of subjects in that sample. That's because we're talking about a distribution of sample means versus a distribution of individuals. And so we will have less variance in that, which is why we're going to divide it by this n. We're not looking for variance, we're looking for standard error. And so that's why we're going to, again, use this divide it by the number of subjects in each sample. So for our expressive group, we'll take 94.44, we'll divide that by 10. For our neutral group, we'll take 111.33 and we'll divide that by 10. When we do the math on each of those, we get 9.44 plus 11.13. When we add those values together, we get 20.57. And this is where we do the square root. So we've done all of the pieces first, and then we'll take that square root of it so that we can get rid of that variance and get down to that standard error. And so we get 4.54 is our estimated standard error for the distribution of means for this comparison distribution. Now, if that seemed like a lot of work for step 2, that's okay, because this is the value that we're going to need in step 4 for calculating our t-statistic. So while it seems like that's a lot of work for just step 2 to describe this comparison distribution, it really is a step that's going to be very, very important, because you can't calculate in step 4 your sample statistic without this value. So now we have all of the pieces of that step 2 puzzle. We have that estimated standard error, that deviation, which would be 4.54. Step 3, we're going to determine the cutoff of that value. Again, we said this was a two-tailed test with p-value of 0.05, looking at our degrees of freedom 18. We're going to use our t-table, and we get plus and minus 2.101. These are the areas that we say these are really extreme scores. These are scores that we would not expect by chance. And we have that 5% split between the two tails. And so we have 2.5% in the upper tail, 2.5% in the bottom tail. And we're saying that any value that is more extreme than either 2.101 or negative 2.101 will be rejected. That those are the ones that are extreme enough that we would not expect them by chance. And that's what we're saying here in our step 3. Step 4 is where we finally get to calculate our test statistic. Here we're using our T formula for independent groups, because we have 2 independent groups, so we need to be able to look at them independently. So we have our 2 sample means, we have our 2 population means, and then we have our estimated standard error that we calculated in step 2. Now note, the whole point we're doing here is we don't actually have our population means, right? We don't actually have that. This is inferential statistics. I don't know the value of mu1 or the value of mu2. But what I do know is what I expect. And what I expect is, in null hypothesis testing, is the null. I'm testing against this idea of no difference. So while I don't know the individual values of mu1 or mu2, I do know that I expect there to be no difference between them if the null hypothesis is true. So I do know that regardless of whatever those population parameters are, mu1 minus mu2 should be 0. So functionally, there's not anything you're going to have to do for that part of the formula. I will include it here to remind us that we are comparing against this idea of no change. But again, functionally, there's not anything that we have to do with that. So then we'll take those two sample means that we had, 79 for our expressive group, minus 68 for our neutral group. We will calculate the difference there to subtract 0, which again, functionally, we don't have to do anything, and divide that by our estimated standard error that we calculated in step 2 of 4.54. That gives us a t-value of 2.42. So we've done all the big math pieces. So all that is left is to put that statistic on our comparison distribution. Is it extreme enough? And make that decision. So our step 5 was 2.42. We put that on our distribution. That is in those cutoff regions. It is more extreme. So we're going to reject the null and support our research in step 6. Now, the next piece that we need is to remember that just because we have a statistically significant effect here, we would not expect this by chance, so we can say it's statistically significant. Remember, statistical significance is not the same thing as practical significance. And so we always want to make sure we're including a measure of effect size as well. For this kind of t-test, one of the easiest ones that we can do is our R-squared value. You're welcome to continue to calculate Cohen's d if you'd like to, but there will be those additional steps to get that the denominator for that one. So here we already have everything we need. So I'm going to take the easy way out, and I suggest for the sake of time sometimes that you often can do that as well. So here what we're going to calculate, we're going to take our t value and square it. So our t was 2.42. We're going to square that value. And then for the denominator, we're going to add our degrees of freedom to that. So this gives us 5.86 divided by 5.86 plus 18, which gives us 5.86 divided by 23.86, which gives us a R-squared value of 0.25. As you can see here, that would be a large effect. Remember, we're talking about magnitude. Here, you're always going to have a positive number because you're squaring those values. But if you did a Cohen's d, an estimated Cohen's d, you can get those negative values. Just remember that we're still interested in magnitude. So it doesn't matter if it's a negative number. It's still a large effect if it's bigger than that cutoff of 0.8 for a Cohen's d. But again, here for R squared, a large effect is anything bigger than 0.25. And we are at 0.25, so we have a large effect. The last piece of this, the new piece of the puzzle that we haven't done yet, is writing an APA style finding. When you read research, they don't just give you this kind of reject the null, fail to reject the null. There is a formulaic way to talk about this, to talk about those two populations, to talk about those differences, to talk about whether it's significant or not, and to talk about about practical significance. And so that's what you see here. So I've kind of given you a little bit of a formula at the top, APA style. You could say participants in group 1, whoever group 1 was, whatever population 1 was, scored different. What's the direction of that difference? They scored more, they scored this different, they scored the same, whatever that case is, on whatever that measured variable is. And then you're going to give the mean for group 1. Then you're going to compare it to group 2, who is group 2, and you're going to give the mean for group 2. Then we want to say that this difference was or was not significant and give a t statement. So we're saying that, hey, we did a t statistic, so we're going to list our t. We need to tell us which t distribution we're talking about. That's where that degrees of freedom comes in. We're going to say whether we were able to reject the null or not. If we're able to reject the null, then our p will be less than 0.05 or 0.01. If we fail to reject the null, our p will be greater than 0.05 or 0.01. And you want to indicate if it's a one or two-tailed test. If you don't indicate if it's a one or two-tailed test, everyone's going to assume it is a two-tailed test. But for the sake of this class and really thinking through the steps, let's go ahead and include whether it was a one or a two-tailed test. And then we want to make sure we talk about practical significance as well, not just statistical significance. And so we're going to say we have a small, medium, or large effect, and give that measure of effect size. So what that looks like for the example that we did in class: students who engaged in expressive writing, mean of 79, had better health scores than those who wrote about neutral topics, mean of 68. This difference was significant. T18 is equal to, that is supposed to be 2.42. P is less than 0.05. A two-tailed test with a large effect size, R squared is equal to 0.25. So that ends our conversation on how we do this for APA style. We will talk in class about confidence intervals. So I want to real quick run through that. You don't have to include confidence intervals in APA style. Sometimes people do. So I'll give you how that looks, but this is the bulk of what is needed for APA style. Again, you can kind of use this formula to write those things out. So if you're in one of my classes, you are more than welcome to write this kind of formulaic APA style format on your formula sheet so that you can use it on your assessments. So for confidence intervals for our writing example, not our jobs example, please excuse that typo. We're going to say we're looking at a degrees of freedom 18. Again, our cutoff values for that is 2.101. Remember, confidence intervals is the flip side of the cutoff values, right? So we say we have 5% in the tails, that gives us 95% in the body. And so we're going to say, okay, well, where do we expect that population mean to be given our sample information? So we are going to rearrange that equation, and what we get is the population mean difference is equal to the sample mean difference plus or minus those cutoff values times that estimated standard error. So for our example, we would have 79 minus 68 plus or minus that's supposed to be 101 times 4.54. We calculate that out, we add it to our mean difference, and that results in an interval around that mean. So we're saying that the population mean difference between population 1 and population 2 falls somewhere between the difference of 1.11 to 20.89. So we're 95% confident that there is a difference between expressive writing and neutral writing in terms of physical health, and the difference between those population means is somewhere between 1.11 and 20.89, 95% of the confident. So that is our conversation on our independent groups t-test. Again, remember, these quick tutorials are refreshers and are supplements to the content we cover in class. Thanks so much, everyone.